Okay, so second talk of this afternoon is given by Simon Arridge, and it's my pleasure to introduce Simon. Simon is a professor of image processing at UCL, where he is also the director of the Center for Inverse Problems. Simon is very well known in the inverse problems community, has developed computational modeling methods for all kinds of forward and inverse problems in medical imaging, in the context of electromagnetic, acoustic, and optical modalities. And in particular, in his recent work, he is very much interested in the interface or the combination between mathematical modeling, knowledge-driven approaches to inverse problems and data-driven machine learning approaches to inverse problems. And part of this he will present today, and the title of Simon's talk is Non-Stationary Blind Deconvolution Using Learned Backward Diffusion. Simon.
Hey, thank you very much indeed for the introduction, Cora, and thank you so much to the organizers for this really great meeting. I'm very impressed with it. You know, being online is always tough, but we've done a really good job in making this almost as good as meeting in person. Okay, so here's an outline of my talk. I'm going to talk about diffusion processes and imaging, learning such things, and show some computational results, and possibly some quite new experimental results with measured data. And the work is related to several things that have been mentioned already in this workshop. Of course, we are very familiar with this idea of learned mapping between spaces X and Y. We've heard much discussion from Rainer Nee, Bruno Forwen, Elena Caladoni, amongst others, about the interpretation of neural networks as PDEs. Also, we've heard from the previous speaker about the idea of solving PDEs with neural net. And I work as a small contribution in this area. We were motivated by a couple of things. Firstly, as Carla mentioned, this general idea about how do we interface between physically known models that are applied over several thousand years of human endeavor to understand the physical world, and purely data-driven models. What's the appropriate way to bring these together? And we're going to hear some more about that in the rest of this workshop. What are the appropriate architectures for learning models, and how can we interpret the set of parameters that we want to look at, that we obtain by learning these models. Actually, a secondary motivation, I should say, when embarked on this work, was we were looking to think about what is a relatively straightforward non-linear inverse problem. There are many inverse problems, for example, as parameter identification, PDEs, that are well known to be exponentially opposed. We were looking for some problems that were not so badly opposed, but were still non-linear. It weren't that easy to define such, but we looked into these ideas of transformations in images induced by variational flows. So it's mostly what I'm going to talk about. Actually, if Carola doesn't mind, I'll steal her favorite quote at this point from the opening to Anna Karenina, which is that happy families are all alike, unhappy families are unhappy in different ways, which we interpret as non-linear, linear problems are all alike, non-linear problems are non-linear in their particular ways. We are therefore going to I will not go as far as to generalize anything about general methods for solving nonlinear inverse problems and just concentrate on some rather specific aspects of this problem I'm considering. Just to mention, of course, as we all know, we have a very popular architectures based on convolutions. And convolutions, we recall, are defined as stationary operations between two functions in L1. So we might ask whether combinations of convolutions, even though we can cascade them and produce multiple channels that feed into each other, are they suited to capture physics for nonlinear problems? And can we improve the interpretability of by using other underlying operations? In a sense, we're asking if we combine our knowledge with physical mappings, can we increase our understanding? Could we improve interpretability or suitability of networks by considering alternative operations? And of course, there's a very large number of previous works. I apologize, it's not time to give fully comprehensive coverage as such, but we've heard in the symposium several books, as I mentioned, about starting with PDEs and interpreting neural networks, particularly in the context of optimal flow. In the context of what I'm describing, we can look at the work by Chen and Hock, which looked into learning optimized reactive diffusion processes motivated by classical diffusion in image processing. And then topics in optimal control by Wine, Tota Haber, and the talks we've heard here, this workshop by Caledoni and Oren. These provide insights into constraining and designing new network architectures based on diffusion processes, which are parabolic PDEs. One thing we note that from these works is that the filters on the networks are localized because by construction they're convolution-like. The one question we want to ask is, can we involve global filters using spatial variation parameters, starting from nonlinear diffusion? We also heard from the previous speaker a really good summary of works on solving PDEs with neural networks, and so physics-inspired neural networks was mentioned. I wanted to mention just this one work which is somewhat related, which is method learning pseudo-differential operators with deep neural networks. This looks at the problem of solving a general PDE characterized by special differential integral operator L parameterized by eta. And obviously, formally, we can solve such a problem by if we can construct the Green's operator as its inverse. And the problem with the conventional operating is that even though the representation of L can be very sparse, using just localized stencils to represent the derivative operators, Gn is usually, G eta is usually huge dense matrix, cannot be stored explicitly. So they asked how to represent the output and how to represent the training data. And just summarizing one or two aspects of that work, they propose representing a decomposition of Q with a wavelet, a non-standard wavelet form, and using learned sparsity reduction operator S. Again, this could be related. I think I don't have time to talk about it, but it might be interesting to discuss is the relation to the reduced basis method we were just hearing about, because it can take samples for a given parameterization eta I, we can take with multiple right-hand sides to obtain snapshots of the fields Uij and use this to learn a sparse representation. Okay, so let's look at what we're really going to talk about here. We're going to talk about the diffusion process on a fixed interval with some diffusivity, and the key point, of course, is that this diffusivity, gamma, is spatially varying, but also it's nonlinear because it depends on the function f itself. So we have an initial state f0, which we can interpret as time zero, input into a forward propagating processing time to end to a final static time, capital T. We'll leave aside the space boundary conditions for the moment. I'll come back to that later. And so we'll make this definition of this operator L gamma explicitly here now in terms of divergence of gamma dependent on F of the gradient of F. And we make explicit that it depends not just on space, but also on time. So looking first of all at the simplification, if we just talk about stationary diffusion, sometimes called isotropic diffusion, if we set gamma equals 1, then the differential operator is nothing more than the spatial Laplacian. And in this case, we know analytically what the solution is because we know what the Green's function is. Green's function is, or Green's operator is a stationary convolution with a Gaussian kernel. And the relationship between the time and the blurring width of the Gaussian is well understood. It's just after time t, one obtains the blurring given by standard deviation square root t. So it means that convolution is going to be a perfectly good model to represent forward diffusion with an isotropic process. This is what it looks like. We just repeatedly apply the convolution kernel, or alternatively we take steps of solving the diffusion equation, progressing in time, just leading to a uniform blurring everywhere. The resulting sequence is known as a scale space because there's a direct mapping between the original R2 function into R2 cross 0t, which gives you this third dimension of scale or time, which is the equivalent interpretation. And when we turn to the nonlinear case, things become obviously much more interesting. So as we said, the diffusivity depends on F itself. And we can illustrate that with a classic example, the Perron and Malik diffusion equation, which was developed as a kind of non-stationary denoising flow process, sometimes known as edge preserving. And here the diffusivity has a particular form in terms of the gradient of F. And lambda, there's a threshold parameter which controls which edges are considered noise. And if you sketch this function, you see that as gradient goes to 0, it becomes 1. As gradient goes to infinity, it goes to 0. It's monotonically decreasing with the increase in the gradient. And this leads us to a flow mechanism which prevents flow across edges. So if you apply the same, if you do the same propagation forward with this flow, we obtain something which tends to smooth out in regions which are homogeneous, or more specifically contain very low magnitude edges, whilst preserving the stronger edges. And of course, there is a really huge literature on this, many, many other flows, which produce different kinds of geometric effects. But they all have this nonlinearity in common. So would networks be a useful mechanism to look at this kind of problem? The problem with such a nonlinear diffusion process is, of course, there's no closed form solution, and solutions need to be computed numerically. In fact, we're following here very much the motivation we heard from Alan Levine and others, just to use a time stepping scheme, which in the deep learning world we would refer to as a ResNet architecture. So going back to this governing equation, we can establish a link between two time steps. T time Tn, we have a representation Fn. We go forward a step delta T. So the result will be got by an explicit integral from Tn to Tn plus 1. But naturally, since gamma depends on f, we can't solve this without knowing gamma explicitly. So we do the classical thing, which we fix over this interval that we're considering and approximate an integral by the length of the interval and the value of the fixed integrand within that step. So from this formulation, this really leads us to a general time-stepping scheme. In fact, to be specific, it goes to the explicit scheme. So we can represent a single step of a forward explicit solver with this new operator D, which we'll call a diffusion operator, which is just the identity and the time step times the differential operator fixed at this particular point in time and applied to Fn. So this is just a linear step in Fn now. Equally, if you're solving PDEs, we know that we can solve that equally well with an implicit scheme, simply by taking the changing the sign of the term applied to the differential operator and inverting this. And the advantage, of course, is that whereas the explicit scheme is only stable if CFL conditions are satisfied, the implicit scheme is unconditionally stable. On the other hand, we only have, because of the nonlinearity with respect to gamma, we only have an accurate solution for sufficiently small steps delta t. But this suggests that we can now construct a scheme, an operator kt, mapping from the initial to the final state as simply the concatenation of these layers, parameterized by a different function gamma at each time step. Well, of course, we'll show some results with this, but of course what we're interested in is the inverse operation. We want to know whether we can learn the mapping backwards from the final state to the initial state. Now, for the isotropic case, the forward problem is stationary deconvolution and the inverse mapping is a stationary deconvolution. And in this case, we can analyze it rather easily. In the Fourier space, we have that the Fourier transform of the final state is the product of the Fourier transform of the initial state with the Fourier transform of itself. So the Green's function operator just becomes an obligation by exponentially decaying Gaussian. And so formally, we could say that the inversion is given by division in the Fourier domain. We take the final state, multiply it by an exponentially increasing Gaussian, e to the positive k squared t, and take the inverse Fourier transform. Now, obviously, if you've ever attempted this, we know that it comes with two very severe problems. Firstly, this factor, exponential k squared t, is so the equivalent convolution in the spatial domain doesn't exist. And we could possibly overcome that by adipizing functional cutting it at high frequencies. But more severely, it's unstable in the presence of even a small amount of additive noise, and so it needs to be regularized. Nevertheless, let's just pursue that for a moment and consider a formal solution. If we divide the time interval into n steps, so that n equals t, then by a Taylor series, we can take each individual step, e to the k squared delta t, and multiply it as a, so expand it as a sequence in powers of k, or powers of k squared, which in the spatial domain can correspond to convolutions with the Laplacian. And so if we truncate that at the first order, we arrive at this operator here, which we'll call a backward diffusion layer operator, which is identity minus delta t Laplacian f, which we will call the Green's function for step delta t, or Green's operator. And obviously, we can recognize that this coincides simply with the inverse of the implicit update. If we look at t delta t implicit there, it has exactly the same form. And so we could formally say even though the inverse operator doesn't have an explicit representation as a convolution because it's unbounded, we could say that the approximation to the initial state can be got by applying this incremental operator n times. And this would actually formally be the case that in the absence of noise, and as we take the limit as delta t tends to 0, we would obtain the exact solution. So now we're going to make a simple conjecture that in the non-stationary case, we can, or there will exist local filters, which we'll call zeta to distinguish it from the forward case, and that we can define this now non-local operator or parameterized by the diffusion operator epsilon. And we will conjecture that if we have sufficiently small steps and we concatenate those operators, it will give an approximation for the nonlinear inversion as well. Just make a comment here, which I found somewhat interesting. In image processing, even in fact in just what you might call analog image processing, it used to be done in a darkroom. There was a technique called unsharp masking, which consists of taking an image, slightly blurring it, and subtracting it from the initial image and adding back a small multiple of that. That's represented in here as the observed data, just an obtained image somehow. It's just blurred, which can be done with an optical system, and then inverted and subtracted, and then added to the original image. And if we just look through the equivalent operations in the Fourier domain, we see that it works because you are subtracting some quantity of the Laplacian of the observed data. But you can actually do that just by analytic convolution. So we can possibly interpret what we're proposing as a sort of nonlinear version of unsharp masking. Okay, so we want to know how that goes in a learning context. So we recall this time-stepping scheme for the, we're going to look both at the forward and inverse problems. For the time-stepping scheme with the explicit diffusion operator consists of adding the spatial derivatives. And then if we interpret each time instance, we just write the layer function as the continuous function sampled times n. Then we can connect the layers by a diffusion layer operator, and we'll say that the learnable parameters are gamma and delta t. So that our equivalent kind of ResNet style operation consists of updating each layer by adding on a small multiple of this special derivative operator L parameterized by gamma. So to implement that, if we were considering images, m squared images, of course we have to vectorize that into a vectorial length m squared. And our explicit diffusion layer operator can be approximated by a stencil. So this is how we would work in a conventional regular grid using finite difference operators. We would construct diagonals, subdiagonals of a sparse matrix, left, right, upper, and lower. Neighborhoods of the pixel will correspond to this structure here, where we have in the center a tri-diagonal format, and then these two fringes off the top right and the bottom left. And importantly, we would require that the diagonal term is the negative of the sum of the off diagonals, so that the operator has a kernel, which is 0. Or, so we could say that this has a 0 mean. So now in the writing in terms of an architecture, we just represent this by estimating the diagonals of an operator L, estimating a time step dt, and then just updating by adding this differential part to each layer. And so this looks familiar as a ResNet style approach. But of course, this is only going to work if we have a fixed gamma. So this would, if our task was to take some unknown spatially variable parameter gamma, we could train a network by diffusing images with this fixed gamma multiple times, and then learning this explicit fixed gamma, and we could even interpret it as time varying by interpreting the layers, but more directly, we could consider that was just an explicit scheme a fixed gamma. So in other words, we would probably interpret the gammas as stationary in time if we were just trying to find a physical process with a variable diffusion. But in principle, we could regard that as a process which was diffusing, where the diffusion was varying in space and time, but always fixed. Oh, doesn't correspond to a physical process that I can think of. But what we said we were interested in doing is looking at nonlinear diffusion, where the diffusivity depends on F. So we need some estimator for gamma. So of course we're going to see if we can construct a network that learns gamma. So the important thing to notice here is that we're not learning anymore fixed gamma. We're learning an operator which derives gamma from an input layer. But nevertheless, we can still do this using any kind of conventional convolutional neural network or any other favorite network that we might have. We might have a multi-scale network, recursive network, as we see fit. But in this work, we've simply used a feed-forward CNN system. Now, what about the inversion task? If we now go to the backward diffusion operator, which we call epsilon delta t, the only difference, as you call, was the reversing of the sign of the spatial derivative step. But as we know, this is not going to be adequate because it has to be regularized. So we'll define this operator epsilon tilde as the sum of this inverse filtering step and a regularization step. So this leads to a more general filter W, which is still going to be represented by tridiagonals, but we remove the mean free condition. So now we're going to have a system which learns 5 subdiagonals, or the main diagonal and the, sorry, in fact, I've just written that should be, the central one should be just written as zeta 5. So it's not, we've removed the mean free condition. So what does the architecture look like? It consists of something that looks at architecture, where we're taking each layer and adding the result of filtration with a linear operator W, but the parameters of W are learned from each layer. So we have our initial state. Now we can, in the forward problem, that's going from the unblurred to the blurred. In the inverse problem, we're going from the final blurred state back to the initial. We apply our lambda theta estimator to derive the diffusivity. It feeds into the stencil of filter W and iterates to the next layer. So the important thing to learn is that we're not learning the zeta. We're learning the parameters of the neural network at each layer, at each iteration. And more specifically, we're using a small feed-forward neural net with 32 channels, and the output is therefore mapping to the subdiagonals. So we're going from input function size of an image to 5 images. Okay, so let's look at some results to see how this is working. I'll be a bit brief with this. I'm not short of time. So let's just do an experiment where we run the programmatic function. Well, first of all, let's run the diffuse function with a fixed gamma 1 times t. And then stable will add none and boundary conditions as well on the boundary. It's a special domain. So this looks fairly easy to understand. We have this example at the top left, a disk. The Gaussian kernel leads to a blurred disk. And when running through this inverse network, we get a good output. And this shouldn't be very surprising, but neural networks are very good at doing stationary deconvolution. And in the Fourier space, we just remind ourselves that the effect of the convolution is to damp the higher frequencies, so the network has to add back high frequencies. And so if we look at, in a little bit more detail, what's happening in those steps, we're starting from this blurred image. We're learning the subdiagonals. So these subdiagonals are represented here, just shaped into images themselves. Actually, this is not actually the function zeta, it's the function zeta multiplied to the initial image. So we see that if you can mentally divide this image by the original function, this is essentially a function which is approximately -1 everywhere in the subdiagonals, and in the main diagonal it has the change of sign, so it's actually the positive sum, or approximate the positive sum of the other diagonals. So it looks very much like an isotropic Laplacian, as we would expect, and the sum of those gives this update step, and it looks exactly like the spatial Laplacian applied to this image. And then we just add that in, just like we would do in unsharp masking, to get the next iteration. And in Fourier space, you see that the Fourier transform of this update has got these increased high frequencies. And again, that's entirely predictable, because the theory would say spatial representation of the Laplacian is just a quadratic function. We're just scaling the frequencies by quadratic function. We go to the next iteration, it starts to become slightly different. We see that actually the updates are concentrating on the edges of the previous step. And we still have something that looks quite like the Laplacian being added in, but actually the functions are tending to 0 in where the image is doesn't have any structure. And if we go on, we get these subsequent iterations, and then finally we just apply positivity, which we call ReLU in deep learning, to give us an output. So this is not particularly surprising, except that we're saying that by using this nonlinear architecture, we can do a conventional kind of stationary deconvolution. So now let's look at how it works on nonlinear diffusion. So again, we go back to this programmatic function, and now we generate training data by running many images through a programmatic forward diffusion model. And then we contaminate with noise. So the training set here is that we're taking this SCL10 database, 100,000 images. We ignore the labeling on it. We use 90,000 for training, 10,000 for testing. And we do a slightly less dramatic amount of blurring by diffusing for 4 time steps with an interval of 0.1. That's a little less than half the amount of blurring in the previous example. So we generate these training sets, and you can see if you look that this has a kind of non-local aspect to it, that some of the edges of the image remain edge preserved, and the small edges are being blurred out. And when we run the inversion, this also works very nicely. Getting this, including 1% noise, we are still getting back very good representations of the input image, the unblurred image. We want to compare this to some other method, so we compare to a standard out-of-the-box architecture, UNet, which is a multi-scale encoder-decoder, which also performed pretty well. And when we look at the residuals, no noise, getting very small errors. When we increase the noise, we are getting obviously some more error. If you look at the fine detail around the high frequencies, we see that we're not so able to get that back when we have noise, and that's not surprising because we are learning some kind of regularization to offset the propagation into the high frequencies of the error. So at this stage, we can say that updates in DiffNet are performed explicitly, and the CNN is only used to produce these filters. This allows a natural way to incorporate constraints such as zero mean, which we can apply or not apply. And so DiffNet needs to learn a problem-specific processing in contrast to purely data-driven. So by incorporating the problem into the architecture, we are making a more specific system. And interestingly, the number of learned parameters is much lower. So in the example shown here, we have about 100,000 parameters, whereas the UNet had about 34 million. So we're using about 1/3 of 1% of the parameters compared to UNet. Let's just look at a couple of other aspects. So before I finish, so we have test error versus training size. If we look at the forward problem, first of all, we see that DiffNet is achieving a higher PSNR than UNet. It's plateauing at around about 1,000 training data size, whereas the UNet is growing more or less linearly. For the inverse problem, it's fairly similar in the absence of noise. When we include noise, we have things that look a little bit different. We see a bit of some jumps in using UNet. We found some overtraining problems going on there. And here they asymptote to the similar performance level, but we reach it with the DiffNet architecture much earlier, with much less training data than we do with UNet. And lastly, let's look at this idea of what the regularization is doing. So we're by removing the mean free condition on the general W, we interpret the difference of the sum of off diagonal to diagonal as a regularization parameter. So we can estimate S by explicitly taking that difference, and then by taking the mean value, we get an estimate for the level of smoothing. And we see rather helpfully that the bottom is cut off there, that's the noise level. We're seeing that the smoothing level is growing exponentially with the amount of noise, which is what we expect. It's rather we're nearly out of time. I'll just mention that we're doing some experimental results. This sadly got interrupted by the pandemic crisis. What we've done so far is to push by observing with a camera through a diffusion medium and using a simple database like MNIST. So here we have this database. We have the observed data through diffusion and a reconstruction, which is fine and not too surprising because that's isotropic diffusion. And so that's stationary deconvolution. But actually also we can do non-stationary for diffusion by using variable density scattering. And don't have much time. If you look at those images, you can possibly see in the middle there that the amount of blurring is varying across the image. And yet the reconstruction is still working. Okay, so to summarize, we're talking about taking physics into account to obtain more expressive and suitable network architectures, allowing by this interpretability to control and constrain operations, leading to a reduction in required parameters and increased interpretability. So I'll leave some of these ideas for the future, maybe to questions. And